Okay, hi everyone. So I'm going to be walking over question 2 on exam prep week 11. So going into this problem, I'm going to expect that you guys have watched the lectures on MSTs. And so if you guys haven't watched the lectures, watch the lectures, make sure it makes some sense, and then come back here. Okay, perfect. So this question states, for the graph above, list the edges in the order they're added to the MST by Kruskal's and Prüm's algorithm. Assumes Prims starts at vertex A. Assume ties are broken alphabetically. Okay, perfect. So let's walk through Prims and Kruskal's, and I'm going to expect that you guys have seen the algorithm in lecture, so I'm going to give an intuitive way of approaching these for an exam setting. Okay, so let's look at Prims, and we're going to start Prims from vertex A. Okay, so how Prims basically works is that we're creating a team of vertices and we need to find the next person to join our team. That's how I like to think about it. And we're lazy, so we want to find the closest person to the team so far. Okay, so far the team is just A, and A is like, hey, I want a teammate. So who is the next closest person to join A's team? Well, it's B, right? Because B is 6 away. Okay, so now the team is A and B, and they're like, okay, guys, we need another teammate. So B's like, okay, the closest person to me is C, who's 3 away. A, is anyone closer than that to you? And then A is like, no, C is 12 away from me, right? So we add C, because C is the next closest person to join the team, right? Okay, so the next thing we do is now the team is A, B, and C, and we're like, okay, who's the next person to join the team? So we see here that the next closest people to join the team are G and E are tied as 4 away. So we break ties alphabetically. So then we're like we're like E, you are on the team. Okay, so now that E is on the team, E is like, hey, my close friend F is like an easy addition to the team. He lives really close to me. Let's add him. So then we add F to the team, right? And then we need to add G to the team now because G is a bit closer than D. So let's say add G first. And then finally, we're like, okay, D, we need one more person, and you're 9 away, but there's nobody else, so let's add you. Okay, so that is basically how I like to run prims in my head, and it does work as an algorithm. Okay, so one more thing on prims before we move on to the next part is I want to talk about this thing called the cut property. This is something that's talked about in lecture, but it's sometimes confusing for students to understand. So let's say that we're at this step in Prim's algorithm. We've added A, B, and C, and we're trying to figure out who to visit next, right? So the reason that Prim's algorithm actually works is because of the cut property. The cut property states that if we have any cut in the graph, we know the minimum weight edge spanning this cut is in the MST, okay? So what that is saying is that we have a cut in a graph. And what is a cut? A cut, visually, looks like this dotted line I made, but more rigorously, a cut partitions the vertices in a graph into 2 sets. So you guys can see this red cut partitions the vertices in the graph into a set A, B, C, and the set G, F, E, D, okay? So with any cut in a graph, the cut property, just to reiterate, says the minimum weight edge along that cut has to be in the MST. Because of that, we know that the BE edge and the GB edge both are in the MST. So I'll clarify the cut property just to be a little more rigorous. The cut property states the minimum weight edge, it doesn't have to be in all of the MSTs, it just has to be in some MST, right? I'll give you guys a reason why. Suppose we have a graph A, B, and C, and assume that all the edge weights are the same. So if we're looking at this cut, notice that in one MST, this is a valid MST in which AC is part of the MST. In another valid MST, we see that AB is part of the MST, in which case the AB edge is selected along that cut. So the cut property is stating that the minimum weight edge along any cut isn't necessarily in all MSTs, it's in some MST, right? Because a graph can have multiple MSTs. So another quick aside, when can a graph have multiple MSTs? A graph can have multiple MSTs if the edge weights are not distinct, okay? But important clarification, if the edge weights are not distinct, that does not guarantee that they are multiple MSTs, right? Okay, this is like really off tangent, but I think it's important information to understand. Okay, so going back to the cut property, the reason prims works is all prims algorithm is doing is we keep applying the cut property every time we want to add another vertex to our team, right? Right here, we have this red cut and we say, who's the next person to add to our team? Which edge is the lightest edge across this cut? So then we say BG and BE both could be chosen. So we choose BE just arbitrarily, right? And now, right, now we see that the cut is going to be a bit weirder than before, but it's something like that, right? So you see that like prims, all it's doing is just repeated applications of the cut property, okay? I don't know if that like is a little too mathy for you and you guys liked my team example before, but if you guys want to understand why it works, it's because the cut property is true, like it holds, and we can apply the cut property to create an MST. Nice. So cool aside. No, okay, so, oh wait, we need this. Okay, let's go back. I want to get back the yellow edges. Give me a sec. Oh man. Okay, perfect. So the yellow edges are, actually we can go in the order that we added them. So it says list edges in the order that are added to the MST. So if we recall, we added AB, then we added BC, then we added BE, then we added EF, then we added BG, and then we added CD. Okay, so what Kruskals is doing, Kruskals is actually like, I think Kruskals is very intuitive. All Kruskals is doing is it sorts the edges from smallest to biggest, and it keeps trying to add the next smallest edge to the MST unless that edge creates a cycle, okay? So let's see what I mean. The smallest edge in this graph is EF. So Kruskals would add EF, okay? I'm gonna fill this in as I'm going this time. Then Kruskals will say, who's the next person we wanna add? Well, let's add the next smallest, which is BC, okay? So we add BC. Then Kruskal says, who's the next one that we wanna add? So we have BE and BG, which are tied at 4. So we'll add BE, breaking ties alphabetically. Then we say, who's the next one we want to add? Well, the next smallest is BG, so we add BG. Okay, then the next smallest is CE. But we don't want to add CE because if we added this green edge, it would create a cycle, right? We see that this orange cycle gets created. Okay, so we don't add CE. So the next one we want to try is AB. And then we see that AB will get added because A isn't part of MST so far. Then the next one we would consider is BF, but notice that BF creates a cycle. So we won't add BF. And then we'll see the next one we add is CD, upon which we terminate Kruskals because all the vertices have been connected to the MST, but another way that Kruskals actually figures that out is we've added exactly n-1 edges. Okay, so we see here that prims and Kruskals can add edges in a different ordering, which is shown by this example. Okay, so the next question states, is there any vertex for which the shortest paths tree from that vertex is the same as your prim MST? Okay, good question. So is there a vertex that has the same shortest paths tree as this MST right here? Okay, let's think about it. So I'm just going to walk through all the vertices because honestly, I think that's how I would probably do it in an exam setting. I would say if I'm starting from D, what's the shortest paths tree from D? Okay, well, the first thing I'd notice is that the shortest path between D and E would go like this, right? And we see that immediately this is broken because the edge CE is not in our MST. So we can eliminate D. We can also eliminate C because C to E is not included in our MST, but it would be in the SPT. Okay. And then we can eliminate E by the same logic because E to C, right, is not part of the SPT. And then we can go to F, and we can also eliminate. Can we eliminate F? Let's see. Okay, so F to E, and then F to B would go like this. Then F to G, F to A. Oh, okay. The reason F doesn't work is because F to C will go via this edge, right? Okay, so with that, we can eliminate F, but that one was a bit trickier. And then B, let's look at B. So B to A, B to C, B to G, B to E, E to F, then we see C to D. Okay, so we see that the shortest path tree from B is the same as the MST. So we can add B. Let's see if A also holds, right? A seems like it should hold just because it's positioned relative to B, but let's double check. So let's get rid of all of these red edges. Okay, so if we're at A, we go to B like this, we go to G like that, we go to C like that, then we would go to E like that, F like that, and then D like that. Perfect. So we see here that A, B both hold, and we can easily see that G also holds because the shortest path from G to any vertex is just 4 plus the shortest path from B to any vertex. Okay, so with that logic, we could say B, E, and G are the vertices for which the shortest path tree is the same as the MST. True, false. Adding 1 to the smallest edge of a graph G with unique edge weights must change the total weight of its MST. Cool question. So let's see. Suppose we have any graph, okay, and we have some MST, okay? That's not an MST. Now it's an MST, okay? So it says adding 1 to the smallest edge of a graph G with unique edge weights must change the total weight of its MST. So the first observation we want to make is that the smallest edge of a graph G must be in the MST, right? Like let's say we have this graph and let's say this edge was the smallest edge in the whole graph. The reason it must be in the MST, this is really, really cool. I'm going to do a proof by Kruskal's. It's not going to be a proof, it's going to be like a 10-second justification. When we have the smallest edge in a graph, we know Kruskal's algorithm produces an MST. So by the correctness of Kruskal's algorithm, the smallest edge in the graph will be added to the MST because the first edge in Kruskal's that we add can't create any cycles, right? And the first edge we add is the smallest edge. So since Kruskal's is correct, and we add the smallest edge first in Kruskal's, we know the smallest edge in any MST is part of the MST. Okay, so we know the smallest edge is in an MST, and also because the edge weights are unique, so there's not going to be any duplicates. Okay, so if we have the smallest edge right here, we know that it must be part of the MST. So if we increase its weight, the weight of the MST must also increase, right? And what's important is that increasing its weight it may not necessarily be in the MST anymore if there's another edge with weight 2 here, right? Because now a valid MST is selecting this edge after we've increased this guy from 1 to 2, right? So like, it's not necessarily always the case, but we know for a fact that the total weight will increase, right? So the total weight will increase. But quickest like the clarification is that the edge may not necessarily stay. Okay. So with that in mind, let's say true, and then a justification just to reiterate, the smallest edge must be in MST, and so increasing its weight increases weight of MST. Okay, the next question asks, the shortest path from vertex A to a vertex B in a graph G is the same as the shortest path from A to B using only edges in T, where T is the MST of G. Okay, so this question is like a lot to understand, but all it's saying is if we have some A and some B, and we have, I don't know, some other vertices, right? In any graph, there is a minimum spanning tree. So it's saying that, like, suppose this is the minimum spanning tree, the shortest path between A to B is the path that we take by traversing the edges of the minimum spanning tree, okay? But this isn't always the case. Assume that, like, these edges are, I don't know, all 2, and these 2 are 3. We see that the minimum spanning tree is taking the green edges, but the shortest path between A to B is by using this orange edge. Okay, and a very common exam question that we like to ask is making these comparisons between MSTs and shortest path trees. And the general rule of thumb, which isn't always the case, is that MSTs and SPTs do abide by a very similar algorithm, but they're different entities and they aren't as like, we can't like interchange them as easily as this problem implies. Okay, so just keep that in mind that these MST, SPT similarity questions are often trying to trick you guys. So make sure that you guys understand why an MST is different from an SPT. Perfect. Okay, so false. And let's bring in this counterexample. Okay, so the last question states, given any cut, the maximum weight crossing edge is in the maximum spanning tree. So what is the maximum spanning tree? The maximum spanning tree in any graph is a tree containing edges that maximize the total cost, okay? And a way that we can like create a maximum spanning tree is that we can just run Kruskal's. Instead of adding the smallest edge first, we add the biggest edge first, right? Like a maximum spanning tree is like basically very, very similar to a minimum spanning tree. We just add bigger edges before smaller edges, right? So because of that, like a couple ways creating maximum spanning trees, just for you guys' interest, is the way I said before, running Kruskal's with biggest edges, smallest edges. We can run prims, but when we run prims, we can find the largest edge spanning any cut. What another way we can do is we can negate all of the edges and then run prims, run Kruskal's, and then flip the edge weights back to positive after running, okay? So in other words, like a maximum spanning tree is actually really, really similar to a minimum spanning tree in that the process of creating them is nearly identical. Okay, so with this idea right here, given any cut, the maximum weight crossing edge is in the maximum spanning tree. And this is true. The reason, like the intuition, which I just like mentioned before, is that a maximum spanning tree is basically the same as a minimum spanning tree. We're just favoring edge weights of higher value than lower value. Okay, the more rigorous justification is that if we're running prims, right, a prims is just a repeated application of this cut property. And we can run prims so that we create the maximum spanning tree. And to do that, all we need to do is just take the maximum spanning edge along any cut each time. Okay, so this is true And we can say that we can run, we can run prims, taking biggest edge along each cut and produce maximum spanning tree. Okay, so I think the answers have a different explanation than this one, so I definitely recommend reading that. But yeah, that is all for question 2. I hope you guys enjoyed this recording and the long aside about the cut property.